In this video, we will cover the topics unit junction transistor and photoconduction. Unit junction transistors, commonly known as UJT, is a three-terminal semiconductor device with a single junction which is extensively used in an electronic switching operations. And normally, for transistors, we have two junctions, the input side and the output side, but here we have only one junction. That is why this type of transistor is called as an UJT. And we can see that from the diagram we can able to find that we have only one junction. And UJT consists of a lightly doped N-type semiconductor bar in which a heavily doped P-type material is diffused on one side of the bar. And emitter is connected to the heavily doped P-type material. Base B1 and B2 is connected to both ends of the N-type substrate. It is as shown in this diagram. And UJT has no ability to amplify, and it is not used as an amplifier. But in general, many transistors are used as an amplifier, but the main applications of UJT is not as an amplifier. And UJT exhibits a negative resistance characteristics. It is decreases in VE for the increase in VC, so which makes the UJT to function as an oscillator. The equivalent circuit of an UJT is shown in the figure, and for any of the electronic devices, whenever we want to make the analysis, then the equivalent circuit diagram will be much useful. And the equivalent circuit of the UJT, from the diagram we can easily understand that how it will behave and how it operates for the input and output conditions. It consists of a PN junction diode which is connected to the internal bulk resistance between the terminals B1 and B2. Here the diode D is connected at the input terminal, that is the emitter terminal, and between these two resistance RB1 and RB2. The voltage drop across RB1 is given by RB1 equal to VBB into RB1 divided by RB1 plus RB2. And this ratio is an important parameter, and in the above equation the ratio of internal base resistance across the base 1, that is RB1, and the total resistance, that is the interbase resistance RB1 plus RB2. It's an important parameter and it is known as intrinsic standoff ratio. And normally its values ranges from 0.5 to 0.8. And regarding the operation of UJT, when the input VE is applied, the emitter current will be cut off due to the voltage drop across the internal base resistance RB1 and the diode potential barrier. So we know that if the UJT want to be, or if we want to make the UJT to conduct, then we have to overcome the barrier potential across the diode and also the voltage across this RB1. If the input voltage is larger than these two voltages, then only it will start to conduct. And normally we call it as a reverse bias voltage, which is given by VR equal to eta VBB plus VD. And when the value of VEE, that is the input voltage, is greater than VR, then the diode is forward biased and will start to conduct. This value of emitter voltage, which makes the diode to conduct, is known as peak point voltage, that is VP, and is given by VP equal to eta into VBB plus VD. The emitter current starts to flow after the peak point voltage, and then we can say that it starts to, or it will come to a conduction state. And if you look into the VI characteristics of the UJT as shown in the figure, here we have three main regions: this cutoff region, negative resistance region, and saturation region. If you look into the diagram, this cutoff region is here, then saturation region is here, and we have the negative resistance region. So normally similar to the other the transistors, here also we have three regions, but one important point to be noted here that the negative resistance we have a negative characteristics curve. So it will make this type of device to mostly used in as oscillators. And also another important thing we have to note down from the graph is that normally we will take the voltage on the x-axis and the current on the y-axis. But here we find that the current is on the x-axis and the voltage is on the y-axis. So these are an important point to be noted. And this characteristic curve is drawn by taking the different base to base voltage. There is a 20 voltage, 15 voltage like that. For different varying voltages, we are taking the reading and we are drawing the graph. And for general operations, normally we have to operate the UJT, the negative resistance region, and after the saturation region, it looks like an ordinary diode characteristic curve, and we have to note down the 2 points, important points, peak point and valley points. Next we see the important regions in the VI characteristics curve. So the cutoff region, till the point A, is this point. The device is in cutoff where the diode will be in the reverse bias condition. Hence the emitter current is almost zero, and we can say that the UJT is not under conduction state. And in the negative resistance region is the region in which the UJT is said to be fired or turned on at the peak voltage P, where the positive peak voltage is greater than our eta into VBB plus VD. And in this region, the holes are injected into the N-type region. So this makes the resistance RB1 to reduce, whereby the value of eta by VB is reduced. That is, the conduction start to flow and the resistance in this region automatically decreases. This phenomenon is known as conductivity modulation, because the resistance of this region is decreases and correspondingly the conductivity increases. When more holes are injected into the N region, it further reduces the eta VBB naturally, and as a result the emitter current increases but PE decreases. So this is known as the negative resistance characteristics, and this is an important characteristics of the UJT, and this phenomenon makes the UJT to operate as an oscillator. And next we have the saturation region, and this region of curve beyond the valley point is the saturation. There is a valley point beyond the valley point. In this region the UJT is in on position and the device will behave as a PN junction diode. That is, VE increases gradually with increase in IE, and for normal general operation we are not going for the saturation region, and since most of the time we are using the UJT as an oscillator, so we have to operate the device, or we have to properly bias the UJT such that this device will operate in this negative resistance region. Regarding the applications of UJT, the negative resistance characteristics is an important parameter. So the negative resistance characteristics makes the device to function as the relaxation oscillator, non-sinusoidal oscillator, and sawtooth generator. The sawtooth generator is an important main applications of the UJT. And it is also used as in switching circuits, and it is also function as a triggering device for thyristor based devices, and it is also used as a timer in. So next we have to see about the photoconductivity. So photoconductivity is an optical and electrical phenomenon in which a material becomes more electrically conductive due to the absorption of electromagnetic radiations, and the electromagnetic radiation may be due to visible light or ultraviolet light, infrared light, or even the gamma radiation. The electrical conductivity of certain material increases when they are exposed to light of sufficient energy. and it is widely used to detect the presence of light and measures its intensity in light-sensitive devices. Certain crystalline semiconductors such as silicon, germanium, lead sulfide and cadmium sulfide and the related semi-metal selenium are strongly photoconductive in nature. Or in short, we can say that it is the property of the material by which whenever light falling on it, the resistance decreases or the conductivity gets. Normally, we know that the semiconductors are relatively poor electrical conductors because they have only a smaller number of electrons that are free to move under the applied bias voltage, and most of the electrons are bound to their atomic lattice in the set of energy state called as valence band. And we know that whenever the electrons are moving to conduction band, then only the conduction will starts. But in a normal semiconductor, most of the electrons they lie only in valence band. So under normal condition, no current conduction will takes place. But if the external energy is provided, some electrons are raised to the conduction band where they can move and carry current. So the photoconductivity results when the material is bombarded with a photon of sufficient energy to raise the electrons across the band gap, that is from the valence band to the conduction band. What happened is that the energy provided by the photons or the photonic energy is absorbed by the electrons which are lying in the valence band. So because of that they gain some energy and they will try to move to the conduction band. Whenever the electrons will moving to the conduction band, then we know that the current conduction will start. Photoconductive cells are the device which is constructed based upon the photoconduction principle is the photoconductive cell. The photoconductive cell is a two-terminal semiconductor device whose terminals resistance will vary with the intensity of the incident light. They respond slowly to changes in light intensity. Light-sensitive material is arranged in the form of a long strip zigzagged across a disc-shaped base with the protective sides. So the construction diagram here will shows that clearly what we are now theoretically what we are telling. For added protection, the glass or plastic cover may be included, and the two ends of the strips are brought out to the connecting pins below the base. So you can find that we have the two pins taken output side to make the connections, and we have the strips like structure here. So these are the made up of photoconductive material, and when the light is falling on this, then we find that photoconduction will take place and it will start to conduct the current. And this is the symbol of the photoconductor, and if you note down, we have the symbol lambda here. So that clearly shows that depending upon the wavelength or frequency of the light, also can able to change the amount of current that is flowing through this type of devices. So for all the devices we have the characteristic curve, and here also we have the characteristic curve which is called as illumination characteristic curve. And the illumination characteristic is observed that when the cell is not illuminated, its resistance may be more than 1 kilo ohm. So in the diagram you can see that the characteristic curve, it has a very large value, and this resistance is called the dark resistance because we are not providing any light intensity. There is a very low light intensity here. So the low intensity light, it will provide a maximum resistance, and that resistance is normally called as dark resistance. And when the cell is illuminated, the resistance may be fall into a few hundred volt. So from the characteristic curve we can find that whenever the intensity of light is increasing, the resistance automatically gets